Hello guys, my name is Calvin with student ID number 22055311140. I am currently on my first year in mechanical engineering major in Udayana University. This presentation is made for the assignment of engineering materials knowledge subject taught by Prof.Dr. Tjokorda Tirta Nindhia, STMT. All the materials that were used in this presentation was taken directly from this book entitled Science of Engineering Materials Volume 2 by Manas Chanda. The content that will be discussed in this presentation is alloy steels, types of cast irons, and wrought iron. The first one is alloy steels. Characteristic properties of alloy steels are specifically due to added element other than carbon. The characteristics in question include increased hardenability, strength, corrosion resistance, wear resistance, toughness, and improved magnetic properties. Though carbon steels generally contain small amounts of manganese and silicon, their effects on the equilibrium diagram are small. Consequently, carbon steels may be considered as binary ferrum-carbon alloys. However, alloying elements present in the alloy steels greatly affect the equilibrium diagram to make the binary iron-carbon diagram inapplicable. The presence of alloying elements may shift the tectonic point they normally have in iron-carbon diagram. Alloying elements can be divided into two groups according to their mode of distributions in two main phases of annealed steel, namely ferrite and carbide, as seen in the table on the left. Nickel and aluminum, silicon, copper, and cobalt are found almost solely in the ferrite phase, while the group 2 elements are partitioned between the ferrite and carbide phase. The contribution of the elements to the overall strength of an alloy steel by strengthening the ferrite is very small compared to the contribution by changing the structure when the steel is heat treated. This is shown in the figure on the right for chromium iron alloys of low carbon content, where the figure shows that air-cooled chromium iron alloys tends to have a much higher tensile strength compared to the furnace-cooled or annealed steels. Different alloying materials will have a different effect on the produced alloy steels. Manganese contributes largely to strength and hardness and has a moderate effect on hardenability. Nickel improves toughness of pearlitic ferritic steels, heat resistance, and corrosion resistance. Chromium improves strength and toughness in low carbon, and improves hardness and wear resistance in high carbon. Nickel-chromium combination increases toughness and wear resistance. Molybdenum improves the high temperature hardness and strength of steels, and also increases hardenability when combined with chromium, nickel, or maybe both. Vanadium combined with chromium with low carbon steels are case hardened. With medium carbon, the steel will have high strength and toughness, and with high carbon, they will have high hardness and wear resistance. Tungsten strongly increases hardenability. Silicon in larger amounts produce electric steels with higher electric resistance and better magnetic properties. When combined with manganese, silicon also increases strength, toughness, and ductility. Stainless steels are the most important ferrous alloys that resist corrosion. They are also well suited for heat-resisting applications, since they are resistant to corrosion by oxidation and have fairly good strength at temperature up to 600 degrees Celsius. Stainless steels contain chromium and nickel combination, or nickel and manganese combination as the principal alloying elements. In addition, there will always be some carbon and silicon and other alloying elements added deliberately to enhance specific properties or present as impurities. Both chromium and carbon determine the stability of austenite and ferrite. The effect of chromium is illustrated on the binary phase diagram of the ferrum-chromium system with no carbon content, shown in this figure. This is a portion of iron-chromium equilibrium diagram. The broken line shows the gamma loop for iron-chromium alloys containing 0.6% carbon. One type of stainless steels is austenitic stainless steels, which essentially is chromium, nickel, iron alloys. The addition of nickel improves certain aspects of corrosion resistance of chromium alloys. The corrosion resistance of this type of stainless steels is usually higher than the other two types of stainless steels, the martensitic and ferritic ones. This type of steels is also highly shock resistant and are difficult to machine. Next is tool steels. The term of tool steels usually refer to high-quality steels used for shaping operations such as cutting, shearing, forming, drawing, extrusion, rolling, and battering, which require high hardness, strength, toughness, wear resistance, and heat resistance for the tooling operation. The classification of principal types of tool steels and their uses are given in this table, where type W is water-hardening high-carbon tool steels and is typically used for hammers, concrete breakers, heading dies for short runs, punches, chisels, shear, blades, woodworking tools, etc. Type O tool steels is a oil-hardening cold work low alloy tool steels and is typically used for taps, solid threading dies, drawing dies for wires, bars and tubes, blanking, forming and trimming dies. Type A is air hardening cold work medium alloy tool steels. It is typically used for thread rolling and slitting dies and to intricate die shapes. The type S is shock resisting tool steels and is used for punches, chisels, hammers, rivet sets. Type H is hot work tool steels and is used for die blocks, die interns, hot extrusion dies, hot shears, and hot forging dies. Type T and Type M has the same function and typically used for high-speed cutting tools. The only difference between them two is only the materials that were used. T stands for tungsten and M stands for molybdenum. Cast iron are basically alloys of iron and carbon containing between 2 and 6.67% carbon. Having almost no ductility, casting is the only suitable process for shaping these alloys. Hence their name, cast irons. The main type of cast iron is gray cast irons, ductile cast irons, malleable cast iron, white cast iron, and alloys cast iron. The first one is gray cast iron. It is the most common type of cast iron, containing 2.5% to 4% carbon and 1 to 3% silicon. A large fraction of the carbon exists in the form of graphite flakes embedded in the matrix. And this gives the characteristic dark appearance. The lower modulus of elasticity, low tensile strength, low ductility, and difficulty in welding of gray cast iron are all due to the presence of graphite flakes. Since tensile stresses are concentrated at the ends of the graphite flakes, deformation or fracture occur more easily. However, gray cast iron also has important advantages. It is a low melting alloy. having high fluidity at casting temperatures and low shrinkage, which makes it well suited for casting into complex shapes. It can withstand higher temperatures better than steels without warping or oxidizing, and is therefore used for doors and furnace parts. The network of graphite flakes provides a considerable degree of corrosion resistance. Gray cast iron is readily machinable due to the lubricating action of graphite. Moreover, the graphite network can damp out vibrations. Gray cast iron thus has excellent damping capacity and is often used as a base for machinery or any equipment subject to vibrations. Second type is ductile cast iron, also known as nodular cast iron. It is produced by inoculating the liquid cast iron. When it is poured from the melting furnace or cupola with a small amount of magnesium, this treatment causes graphite precipitation in a nodular, almost spherical form. Unlike the graphite in a flake form, spherical graphite structure doesn't produce severe stress concentrations. Thus, nodular cast iron has a much greater ductility and a higher tensile strength than exhibited by gray cast iron. The graphite nodules also serve to lubricate cutting tools and thus provide high machinability to nodular cast iron. Next one is white cast iron. To produce this cast iron, which contains carbon in a combined form as cementite, the total carbon content is kept between 2 and 2.5% carbon, and the silicon content is kept below 1%, and the casting is cooled rapidly. Because of the presence of cementite as a continuous network, white cast iron is extremely hard, abrasion resistant, unmachinable, and unweldable. Malleable cast iron is produced by a special heat treatment of white cast iron, namely heating at about 950 degrees Celsius for nearly 50 hours, followed by slow cooling, which causes cementite to decompose to ferrite and carbon in the form of graphite, and in the form of rosettes or clusters embedded in the ferrite matrix. Because of this microstructure, the metal has much improved malleability, and hence the name malleable cast iron. The lubricating action of graphite clusters also imparts high machinability to malleable cast iron. The lower melting point of malleable cast iron and its greater fluidity at the casting temperature makes it much easier to cast than steel. Alloy cast iron, as the name signifies, are produced by adding suitable alloying elements to cast iron. The effects of those alloying elements, which are used singly or in combination, are similar to those in alloy steels. The last one is wrought iron. Wrought iron is essentially the composite material consisting of high purity alpha iron and slag. The carbon content of the iron is generally below 0.08%, and the manganese content is below 0.06%, while the slag content usually varies between 1 to 3% by weight. The slag is mainly iron silicate and exists as a fibrous structure embedded in the ferrite matrix of rolled and shaped wrought iron. When broken with fracture, wrought iron does show a fibrous break, resembling a break in a piece of hard wood, in contrast to a crystalline or granular break of steel. The mechanical properties of wrought iron are essentially those of pure iron. However, due to the presence of fibrous slag, the tensile strength and ductility are greater in a longitudinal or rolling direction than in a transverse direction,